applications for solving systems of equations. We've got through 6 examples. We got 4 more to get through. And what we're going to do is share that screen and then start with example 7. Some of these examples require a little prior knowledge. Some of them don't. Some of them might be best work with a chart or a picture. Okay, so you want to be versatile. You want to be have a wide variety of problems kind of practiced under your belt, so to speak. And this one I like a drawing for. Randall's going to be building a backyard fence. Maybe he's got a new dog at the house or something. And so part of this is going to be built upon his house. Okay, so there's the wall of his house right there. You guys make this drawing in your notes. And what he's going to do is he's going to build a rectangular yard, and he's got 125 feet of fencing to do it with. So, for example, he could do 5 feet, 5 feet, 115 feet, right? Have a real long, skinny yard. Or he could do, like 12 feet, 101 feet long. So this is there's obviously a variable nature to this problem setup. If we just had 125 feet, he's got endless opportunities or endless options. But the other thing that we want to keep in mind here is that it's limited because look at this sentence right here. It says he wants the length to be 5 feet more than 4 times the width. Okay. So like, for example, if I put down, we're in the habit now of using 2 variables. If I put down width and I put down length as my 2 variables, those 2 variables tell me I need to be able to write 2 what? Equations. 2 equations. Very good. And so my first equation is going to be W plus L plus, there's one more W over here, right? Plus W equals 125. Right? That's that first piece of info that we worked with. And I'm going to ask you guys to help me come up with the second equation. Okay? Tiago, what do you think? It's highlighted in yellow. What do I do? So he wants the length to be 5 feet more than 4 times the width. Okay? 4 times as long as it is wide. That's very good. Now, in my mind, there's a couple things that we need to do. Number one, we need to kind of clean up that first equation, right? How can I clean up that first equation? What do you think, Jake? Yeah, let's just say instead of W plus W, let's just say 2W. All right, so combining like terms. And then, does anybody see, actually, I'll leave it like this. This would be fine for spacing. Does anybody see what technique lends itself nicely to this? Like, Nate, would you want to use graphing, substituting, or eliminating, for example? I'll let you pick. You want to eliminate. Which one do you want to eliminate? Oh, you want to substitute. Why'd you change your mind? That avoid. The second equation is set up, ready to go, prefab, if you will, for substitution because it's got one of the variables by itself. Remember, in substitution, our first step was, hey, pick a variable and get it by itself. If they've already done that for us, then, man, well, let's do that. Let's take and we'll plug in place of L in that first equation. We'll plug 4W plus 5. Okay? Does that make sense? Because the length, and truth be told, fellas, I 9 times out of 10 when I'm doing these types of problems, I would have already done that on the picture. I would have read that highlighted yellow sentence, and I would have just drawn the picture and said W is the width, and 4W plus 5 is the length. And then I would have my picture telling me or dictating for me what I need my equation to be. All right, so 4W plus 5 is the length. But if you look at the picture, it should be pretty obvious. You got W plus 4W plus 5 plus W. How many W's is that all together now, if we combine like terms again? Good, we got 6W equals 120. Jack McBee, where'd the 5 go? Yeah, I subtracted it to the other side. Good. George, what do you want to do to both sides? Divide by 6. And what is that, 20? All right, so 20 is not my answer. It just tells me that that's the width. So what's the length? How do I find the length out, Mossy? What do you think? Yeah, look down at my picture. 4 times 20 is 80 plus 5 is 85. That's why I really like a picture for these kinds of problems, because we can visually, we can see what we're doing there, and we can adjust. It said find the length and the width, so we've done that. The width is 20 and the length is 85. Any questions on that one? That's a real simple kind of setup if you see the drawing and if you recognize, oh, what we've got going on here. Any questions at all? All right, let's move on to example 8. Example 8 is going to be a dirt problem. Drew, what do I mean by dirt? Distance equals rate times time. That's what's operating in the background here. Let me give myself a little bit more room. That's what's operating in the background of this problem. It's prior knowledge. It's expecting us to know that distance equals rate times time. Before I even get into the dadgum problem, I know that because I see 65 miles per hour, 78 miles per hour. I see somebody's driving on the interstate. To me, that's uniform motion. That's distance equals rate times time. And it ought to jump off the page at you as fast as that. Okay, you thought you ought to click and say, dirt problem right here. All right. Now, here's the rundown. We've got John, who's leaving St. Louis and going to Denver. And we've got Kelly, who's leaving St. Louis and going to Denver. Kelly leaves a little bit later, but they both leave at the same position and they both travel the same route. And the question says, when will Kelly catch up with John? So what do you know about their distances? They are equal distances. This isn't one of those dirt problems where we're adding the two distances up and setting it equal to a total. This is one of the dirt problems where we say his distance and her distance, they equal each other's. Okay. Now, I'm going to use a chart. I like a chart on this one. Okay. So we're going to give John a row. I'm going to give Kelly a row. And somebody might in the back of their brain be thinking, well, Coach Morgan, how do you know when to use a chart and when not to use a chart? All right. On most dirt problems, I recommend you guys, at least initially, I recommend you guys set up a chart. Okay? Now, I'm Mr. Coach Morgan, professional mathematician extraordinaire. I probably, if I were doing this, I wouldn't go to the trouble of setting up a chart because I've done a million of these and I've practiced enough to know what to do. You guys are students and you're just kind of first learning how these work. A chart is a great learning tool for that. Okay? It's a great way for you to organize the info. We got distance equals rate times time. I'm going to put that in reverse just because of my habit. Or rate times time equals distance. Okay, because I like my distance to be on the right in my chart. Okay, so it says, how fast is John driving? Do we know that? Yeah, 65, isn't it? And Kelly's driving 78. Now, let's see here. Let's talk to me about their time. Who is driving longer? Who has a longer drive? Who is it? John does. So I'm going to here's a little trick. I'm going to let Kelly's time, okay? I'm going to let Kelly's time be my variable. Okay, I'm going to let Kelly's time be my variable. Now, truth be told, in this section, I'm teaching you guys how to solve systems of equations with two variables and two equations. But this is so simple. I really wouldn't go to the trouble of setting up an alternate variable on this one, right? If Kelly's time, which is smaller, is x, and we were told that she left a half an hour later than John did, that means John is driving a half an hour more. So what's a half an hour more than x? X plus what? X plus what? 30 minutes. Why, Reed? It's half a what? An hour. And what is the rate in terms of? Miles per hour. So we have to make a big fat mention of this. And I'm not going to take time to write it down, but you will. Make sure the unit of time matches the unit of speed. In other words, if I had said x plus 30, I would be way off on this problem because the speed was in terms of miles per hour and the time needs to be in terms of hours. Okay? Now, what do we do from left to right? We multiply. So we got 65x plus, what was it, 32.5? And then here we got 78x x. And what did y'all tell me to do with their distances? They're the same, so let's set them equal. That's how we're going to write up our equation. We'll take this and we'll set it equal to that. All right, and that's my equation. 65x plus 32.5 equals 78x. Now, if you're saying, but Coach Morgan, we want two equations. Okay, fine. If you wanted two equations, maybe we could have let John's time been y. Those two equations would have been 65y equals 78x, and then also y equaled x plus 0.5. And what method would have lended itself nicely? Substitution. And we could have just substituted x plus 0.5 in for y, which is exactly what we have already accomplished. So I don't want you guys being math robots saying always use two variables. If you can get away with just using one variable and it's very, very simple and easy, then do that. Okay? Do that. If we want to solve this, please just subtract 65 over there in blue. Subtract 65x, and we get 13x equals 32.5. Divide both sides by 13, and we should get 2.5. Okay, 2.5. Now, we want to make sure we answer the question. So what did 2.5 stand for? What was X standing for? Kelly's time. She took her 2.5 hours. What are they asking? They say, how long will it take Kelly to catch up to John? So that does answer our question, right? We do want to make sure we always answer our question. Like if the question had said, how long will John have been driving by the time Kelly caught up with him? We would have to say what? 3 hours, because Kelly drove 2.5 and he had a half-hour start. Okay, dirt problem, makes sense? We're about to get to a tougher dirt problem. Y'all might not have seen the next kind before. I love it. It's a good kind of question. Here it is. A river cruise. Makes me think of my cookie joke. Did anybody go home and try and tell their parents the cookie joke? You did, Joey? Did you wait till the next day, or did you just hit them boom, boom? Boom, boom. I've tried it both ways. I can't decide which way I like, because if I do it boom, boom, I get the immediate gratification, but the cookie is still fresh in their mind, and so I don't know. But how did it go over? Okay. All right. Well, the reason that this one is going to be a more challenging example is because, yes, it's a rate, time, and distance question, but the rate of our cruise ship is not, there's more than meets the eye. We'll say it that way. Okay. So I'm going to draw a little picture of a river here, and we're going to talk about the words downstream and upstream. All right. So my river is flowing on my screen from left to right. So it's going from left to right would be going downstream. Downstream, write this down. Downstream is when you are going with the current. You're going with the current. Upstream, you know, salmon, they swim upstream to spawn. That's a phenomenon in nature. Dun, 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 dun. Phenomenon. Dun, dun. Nobody? The Muppets? No. Okay. Anyway, the notion of going upstream is where you are working against the current. So suppose I can swim. Suppose I can swim 5 miles an hour. They'd be booking it as a swimmer. Suppose I can swim 5 miles an hour, okay? And the river that I'm in is flowing 3 miles an hour, okay? If I'm swimming with the current, then my normal Coach Morgan muscles are going to be putting me 5 miles an hour. And then the river is going to be adding to that 3 miles an hour. So to an observer on the bank, I'm going to be going how fast? 8 miles an hour. How did we get that? You add swim speed plus the current. What if I'm swimming upstream? I would only be going 2 miles. We subtract. That's very intuitive, isn't it? Okay, so what I would be doing is I'd be swimming against the current, and my 5 miles an hour would be getting slowed down. There's I don't know if you guys watch UFC fights or MMA, or if y'all are into that bag. But there's a famous guy named Khabib with a crazy last name that I can't pronounce. Khabib is like the bee's knees at this ultimate fighting stuff. And he likes to train by swimming in a river, and there's a viral video of him just bare-chested out in this cold river in looks like Russia or wherever, I don't know. But he's swimming upstream, and it's like he's swimming in place, and he is getting after it, like just minute after minute after minute swimming, and he's not moving anywhere because his swim speed and that river's current, they equal each other out. So he's like swimming in place. It's like the endless pool. If you've ever heard of the endless pool, it's a fancy, it's like a treadmill for swimming. All right. So the idea is that if I'm going with the current, I'm going to add my speed plus the current. If I'm going against the current, if I'm going upstream, I'm going to subtract. Everybody understand that? Okay, the same thing is true. Our next problem will be about an airplane. The same thing is true about a headwind and a tailwind. A tailwind is helping me, okay? James's dad rides bikes a bunch, right? And I bet he loves when he gets a good tailwind, right? Because that tailwind, if I can normally ride my bike 20 miles an hour and I got a good stiff tailwind, I'm probably going to be riding 25 miles an hour, man. It's going to be great. But then if you plan your ride accordingly, it's always a smart idea to end your ride with the wind when you're tired and you're coming back home and it's like, oh, you do not want a headwind, because what's that headwind going to do? It's going to subtract from your speed, okay? It's going to be slowing you down, blowing against you. So headwind slows you down, tailwind speeds you up. Addition, subtraction, just like the current, okay? Now there's a cruise ship in this picture coming off of a dock. Y'all don't judge my artistic prowess here. There's the cruise ship, okay? And it's going to go 60 miles downstream and then 60 miles back upstream, all right? 60 miles down, 60 miles back. Now, if I wanted to organize, I told you guys in the last problem, I like a chart for dirt problems, right? If I wanted to organize this, let's go down stream and let's go upstream. So we'll give a row for each of these. Rate times time equals distance. You know that. Don't we already know the distance is 60? Going downstream and coming back up? That's nice, isn't it? We know the distance. What else? Candy Otto, what else do I know? Very good, very good. So here is where our unknown comes into play. Now, the rookie mistake, check this out. The rookie mistake will be like, yeah, I'll just do downstream is X, upstream is Y. Lewis, did I see a hand up with a question? No? Okay. The rookie mistake would be to say, yeah, we'll just let X be the downstream and Y be the up. No, we're not going to do that. Because we need to come up, if we're going to use two variables, we need to come up with two what? Two equations. So check this out. I'm going to declare my variables. I'm going to say let B be the boat's speed or the ship's speed or whatever. And I'm going to let C equal the current's speed, how fast the river is flowing. And what did we say when we're going downstream? What do we do with those two values? Good. We add them up. So it's going to be B, the boat, plus C, the current. And then coming back upstream, it's going to be what? Subtraction. It's going to be B minus C. Have y'all seen these kinds of problems before? Have y'all done this kind of dirt problem? It's classically sort of an Algebra 2 problem. We see it a lot in Algebra 2 when you guys are, hopefully when y'all are sophomores and you're taking that class. But the same principles that you and I have talked about here in Algebra 1 apply. Okay, what do I do from left to right? I multiply. So guess what? My first equation right here, we'll do our equations in green. My first equation is going to be B plus C, that's rate, times 4, that's time, equals 60, and that's distance. And then we're going to have B minus C, that's rate, times 5, that's time, equals 60, and that's distance again. Okay. Now, yesterday, one of my freshmen, I asked him the following question. I said, hey, what do you want to do to this system now first to start it off? And he said, oh, yes, let's use elimination. Let's kill off the C's. And I said, not so fast, deadgum Skippy John Jones. You can't do that yet. We got these parentheses, and something's being done to the parentheses. What do you want to do now? And then he fell into my trap. He said, oh, well, let's just distribute. And I said, distribute. Don't distribute. Why don't we divide? In the top equation, let's divide both sides by 4. Watch what that's going to do. That's going to produce a new top equation. Do y'all know what 60 divided by 4 is? All right. How about this second equation? What do you want to do to both sides? Divide by 5. Do you know what that is? And now, oh, mama, this is a good system now. It is set up, ready to go for what technique, Grove? Elimination. We are going to eliminate the C's. So we get 2b equals 27. Therefore, b equals 13.5. So our boat's speed is 13.5 miles per hour. All right. How do I figure out the current's speed? If the boat's going 13.5, what could I do? Check. Yeah. And that's one of our options is make sure you heard that. We could take 13.5, we could plug it in to any of the equations. For example, if I plugged it in right up here, 13.5 plus C equals 15, you guys would automatically tell me, oh, Coach Morgan, C equals, did somebody just say daggum 28.5? 13.5 plus what equals 15? 1.5. Good googly moogly. All right. So that's one way of doing it. The other way of doing it, by the way, we've answered our question now. The other way of doing it, instead of plugging it back in, would just be to eliminate the other variable, right? To eliminate the other variable. So like, check this out. What happens if I try to eliminate my C variable, my B variable and solve for C? I could just subtract, kill off the B's. I got 2C equals 3, or C equals 1.5. Okay, either way you slice it. When you're using elimination, I've taught you guys how to use elimination. When you're using elimination, you can eliminate, kill off one variable, solve for the first answer, the half your answer, right? Once you get that number, you can either plug it back in or you can eliminate the other variable. You got 2 options. You get to do whichever one you want. Okay? But now we've answered the question, and that should make pretty good sense. How fast is the boat and the current all together traveling downstream? 15 miles an hour. And how fast is it traveling upstream all together? 12 miles an hour, right? Those were the 2 numbers, by the way, that we got right there. Okay? So I've had students before that say, Coach, couldn't you just average those 2 and get the boat's speed? And the answer will be yes, when everything is level on both trips. In other words, both trips were 60 miles, right? But if let's say this cruise ship went 60 miles down and then it didn't make it all the way back and we wanted to stop, then I could not just do a simple average, okay? So there are shortcuts every once in a while, but they don't always apply, okay? Here's our last example, and I want you guys to try this one on your own. It is a challenge, okay, but you can do it. It works almost exactly like the previous example. Okay, you guys give it a shot, see what you can do about the jet flying in a tailwind and the jet flying in a headwind. I like how I'm seeing people use charts. It's a great idea. And remember how to set your variables. Don't just say, oh, I'll let X be the speed flying into the wind and Y be the speed flying back. You want one of your variables to represent the jet's airspeed and one of the variables to represent the wind's speed. Maybe like a J and a W or something like that. A couple nights ago, I made a breakfast dinner, blueberry pancakes and bacon and eggs and all that. And this morning I got up and I thought, I'm going to finish those off. So I had a couple blueberry pancakes and 4 pieces of bacon. Oh, it was so good. It's a good way to start your day. Lewis, are you a big breakfast eater? Will Edwards, what about you? Are you a pancake or a waffle man? Torn between the two. You know, a house divided against itself cannot stand. My wife is a waffle lady, and I'm pancakes all the way, baby. Flapjacks for life. But we survive. We manage. And since I do most of the cooking, we eat pancakes a lot. All right, you guys have had time to ponder this. It might not completely be finished just yet, but I want to give you a couple of vocabulary words. You heard me use one of them a moment ago. The word airspeed, or the phrase airspeed. I don't think it might be one word. Airspeed is defined as the speed of a plane regardless of the wind. In other words, with no wind, just how fast can that plane go on its own? That's what's called airspeed. How fast a plane can go on its own without taking wind into consideration. That's airspeed. Okay. Ground speed is the speed of the plane from a perspective of somebody standing on the ground, where I would be like if I had a radar gun, I was clocking that plane going by. That's taking into consideration both the plane and the wind. And so when we look at rate times time equals distance, right? And we think about it with he started with the tailwind and then he went into the headwind coming back, right? That rate is going to be the ground speed. Okay. In other words, I need to take into consideration the jet plus the wind. Or when he's coming back against it, the jet what? Minus the wind. Okay, you see what I'm saying there? That's like if we're sitting there watching the dude swim, we have the perspective of watching him swim with or against the current. We're taking into consideration both of those parameters. In this context, we're taking into consideration both the speed of the plane and the speed of the wind. Okay. Now it says for 3 hours he did this and he covered 1,095 miles. Coming back, he flew for 3 hours, but he didn't cover as much. So obviously I'm not going to set their distances equal to each other, but we do now have our two equations. Okay. What do you want to do to both sides of that first equation? Yeah, divide it by 3. I'm going to go ahead and knock that out so that my system can be adjusted. What is 1095 divided by 3? 365. And then 987 divided by 3 would be what? 329. Okay. Now, what technique should I use? Elimination. Let's kill off the W's. We got 2J equals what? 694. Divide that by 2. And we got what? 347? Is that right? 347? Now that's the jet's speed in still air. That's the jet's airspeed, okay? Now we wanted to find the jet's airspeed, but we also wanted to find the wind's speed. So check this out. As I mentioned a moment ago, 347 is smack dab in the middle. It is the average of 365. And it is the average of 329 and 365. So how high up would I go to get to 365? How far down would I go to get to 329? 18, yeah. Now we could get that by plugging it in as we just kind of did, or we could get that by eliminating the J's, whichever way you want to slice it. 347, y'all can't see that anymore, can you? 347, right, would go up 18 to get to 365. It would go down 18 to get 329. So that 18 is my wind speed. The wind is helping it or hurting it, okay? Now, those examples that we just looked at over the last 3 lessons, okay, all of those examples fit into one of 3 categories. Either direct translation, where you're just reading the English and turning it into math, a geometry problem, like we talked about with our triangles, remember? Or uniform motion. Those are our dirt problems. In our next lesson, we're going to get into what are called some mixture problems. We're going to revisit the notion of mixture problems through the lens of 2 variables and 2 equations, okay? In the meantime, if you have not been doing your delta math, please, please, please take care of that, okay? And there in our text, right, remember how we do our OpenStax textbook? Look at all the practice problems that they've got for us. So in the meantime, I want y'all to pick some practice. There's like a problem with the complementary angles. I want you guys to pick some practice problems and put yourself to the test. Say, hey, what if Coach Morgan, wink, wink, what if Coach Morgan gave me a quiz on these kinds of word problems? How would I do? And you can work the odd numbered problems because Bob has the answers. Who is Bob? The back of the book. So you guys, our lesson is over. I'm going to ask you to pack it up, pack it in. And I want to encourage you guys, again, hint, hint, wink, wink, practice some of these problems. Question? It's at the end of section 4.2. So like if you're on, I don't have it pulled up online just yet, but if you went to OpenStax and went to our textbook, it's at the end of section 4.2. All right, you guys that are online, hope you'll have a great day. You guys that are here in person, y'all skedaddle. Live Jesus in our hearts. Awesome. Thank y'all so much. Have a wonderful day.